I would now like to introduce our first speaker on the Kamchatka earthquake, Zoe Yin. Dr. Zoe Yin is a PhD in geophysics and is an expert on geodetic observations of earthquakes or plates and studies large earthquakes, models their behavior and so forth. She's a Mendenhall PhD postdoctorate at doing postdoctoral studies at the US Geological Survey in Golden, Colorado, and has just written a very interesting paper on the impact of the Kamchatka earthquake from the perspective of the USGS system. And I would like to now turn it over to Zoe to tell us about the earthquake. Thank you, Zoe.
Great, thanks for that introduction. Let me see if I can share. Can you see my screen okay?
We can, yeah. And that you're okay. on the presentation, that looks great.
Okay, great. Excellent. All right. Thanks, John, for that introduction. And I'm really excited to talk to you today, like John said, about the USGS response to this magnitude 8.8 earthquake that we saw in July of last year. I'm a postdoc with the US Geological Survey, and the work that I'm going to talk about today is very much a collaboration between all the folks that you see listed here. And so I just want to mention that a lot of the work I'm going to show is going to be the work from these folks here. So I'll start with the big headline, which is that in July of last year, we got a new number 6 largest magnitude earthquake that we've instrumentally observed on our planet. And so earthquakes this large are rare, and it's rare that we get to observe them. So it's kind of exciting from a geophysics perspective to dive in and see what we can learn from this event about what's happening in these complex subduction zones. So I'd like to zoom into the region where this earthquake happened. So here we're sitting at the boundary between the Pacific plate and the North American plate, where, like John mentioned earlier, this Pacific oceanic plate here is subducting beneath the North American plate and generating large earthquakes. So we've seen 2 major earthquakes on this subduction zone. The first one was in 1952. We saw a magnitude around 9 event occur off the coast of the Kamchatka Peninsula here. This is the 5th largest instrumentally recorded earthquake. And then obviously in July of last year, we saw a magnitude 8.8 earthquake occur really close by, indicated by the red star for the 1952 event and the yellow star for the 2025 event. So what I'd like to do in this presentation is kind of take the lens of response, so take the lens of the USGS response to this event, and kind of go through all of the products that we produced to describe what we know scientifically about this event. So that includes the finite fault model, which is a description of the source of the earthquake and the slip at depth. The shaking, which is comes from the USGS shake map, which is informed also by felt reports called Did You Feel It reports. We can talk about estimations of ground failure from the USGS ground failure map, impacts from the pager alert product, which estimates economic losses and fatalities. And then hopefully at the end, we can bring it all together and talk about what do these products tell us about the earthquake and how does that impact our understanding of ongoing hazard in this region. So before we get started, a quick caveat is NEIC, so I don't think I said in the last slide, the NEIC is the National Earthquake Information Center, and we do 24/7 monitoring of global seismicity. And so the kind of philosophy around releasing products at the NEIC is that we release products as soon as data is available to support them. And then as more and better data becomes available, we release new versions of products. So for example, here we can see in the purple for our finite fault product, we start with a kind of a very smoothed version of the slip distribution. And then through time, as data becomes available, it becomes more detailed and changes a little bit. So I'll generally today be talking about the most recent products that we have available, but just know if you're looking at our event pages, if you're looking at our data products, they are going to evolve through time as more data becomes available. Okay, so I'll start with the slip distribution. So often as geophysicists, we want to know after an earthquake happens, what was the slip at depth on the fault that was driving that shaking, that seismicity. And so we use geophysical observations. In this case, we use teleseismic broadband data. We use InSAR data, which is a type of satellite remote sensing data that senses deformation at the Earth's surface. And then GNSS data or GPS data to show static offsets at the surface. So you can see we have two GPS stations or GNSS stations here that are close to the rupture. And so we use these observations to invert for, or to solve for what slip is happening at depth. So you can see our slip inversion is shown here in these kind of white to purple colors. And these types of data products, these slip models are important both in response. So they're, for example, they can be used as the input to modeling the tsunami, and also in long-term hazard calculation. So for example, we use these types of models to track the stress accumulation on subduction zones and locking. So in this case, for the Kamchatka event, we saw an inversion that showed about 190 seconds of slip duration, which is pretty typical for an earthquake of this magnitude. We saw a unilateral rupture to the southwest, which just means that the earthquake started here at the gray star, and then slowly through that 190 seconds moved to the southwest. And we actually saw the largest patches of slip here at the farthest southwest end of the rupture that were kind of strongly constrained by this GNSS station SKUR here to the southwest. Next, the shaking distribution. So this is primarily distributed through a product we call the shake map. So that's what you can see here. And it's using a rupture plane. So in this case, these black squares are indicating the extent of slip based on the slip model that we looked at in the last slide. And we're using that to predict the shaking distribution throughout the region. So these colors are indicating our estimates of what shaking should be. And these are typically constrained by any observations that we have available. So in this case, this is a sparsely populated region and a region that it's difficult to get data from. So we had about 120 Did You Feel It reports. So these are reports that people who experience the shaking can submit, and they can be mapped to approximate intensities. So we had about 120 of those reports that are constraining the field of shaking. And then we also have some really limited regional strong ground motion data. So we have strong ground motion stations that are collected by the Kamchatka Regional Seismological Center. And you can see here, they're just reported as peak intensities as modified Mercalli intensity MMIs that are then used to constrain the shake map. Okay, so we have a product that we also use called the ground failure product to estimate landslide extent and severity. So this combines the estimated shaking from the shake map with some kind of landslide susceptibility model to estimate the number and the extent of landslides. So for this earthquake, we reached a red alert level. So we expected over 260 square kilometers of exposure to landsliding. And actually, a couple of folks, Alex Grant and Elaine Collins here at the USGS, did a really cool study looking at Sentinel-2. So this is satellite optical imagery. And they used that optical imagery to map landslides along the coastline of this Kamchatka Peninsula. And they mapped at least 346 landslides over this region. And so far, the comparison between these two things suggests that our landslide model probably overestimated the number and extent of landslides a little bit. And that's probably because the model, the data that our landslide model is trained on fewer subduction type earthquakes. And so that's something that they're looking at improving in the future. Just for a kind of a ballpark comparison, so far it looks like the number of landslides mapped for this earthquake are pretty similar to those mapped for the 2011 Tohoku, Japan subduction earthquake. Damage and losses. So we use PAGER, the Prompt Assessment for Global Earthquakes for Response product, which again combines those estimates of shaking from the shake map with information about population density and regional construction practices to estimate fatalities and economic losses. So we estimated 10 to 100 fatalities and more than $10 billion in damage for this event. So that's a yellow alert for estimated fatalities, a red alert for economic losses. And when we compare that to what we kind of observed from reported damage, there was only one indirect death reported in Japan from the tsunami evacuation, which I'm sure others will talk about. But most of the damage was reported in a city of Severokurilsk, which is on one of the northernmost Kuril Islands. And it was really extensive damage there. There was reports of almost all the buildings having damage and a tsunami that destroyed a fish processing plant there. So you can kind of see from the discrepancy here between the pager estimates and the reported damage that the pager product likely overestimated the true fatalities and economic losses from this event. So there's two possible reasons that this could be. One is just the uncertainty in the true shaking exposure, because there is just limited data availability and nearby instrumentation in this region. The second one's kind of interesting, and it's that after the Kamchatka Peninsula entered the 1952 event, there was a lot of rebuilding that happened, particularly in Severokurilsk, which actually was completely destroyed in the 1952 event and had to move further inland and was presumably built to a more modern standard and with kind of earthquakes front of mind. And so because pager uses past events to calibrate losses, they don't consider those potential improvements in the building standards that may have happened as a result of past earthquakes, but it should, if there were to be another event here, would do a better job kind of estimating these losses. Okay, so that's all the data products that I'm going to talk about for now. I'd like to spend just a couple of minutes talking about what these information products imply for the seismic tectonics, for the ongoing hazard in the region. So one kind of big picture way that we often think about subduction zones as geophysicists is that these major megathrust events will release most of the accumulated stress and must be kind of reloaded by the subducting of the slab in order to produce another great earthquake. I mean, it's a very rough heuristic, but it's one that I think that often is a mental model for geophysicists. So we can do a quick back of the envelope calculation and say if there were 8 millimeters per year of convergence over the 73 years since 1952, we would expect no more than 6 meters of slip deficit to be accrued if the complete was completely locked the whole time. Yet we see in our slip model that we expect regions with over 30 meters of slip. So there's kind of a discrepancy there. One reason that this could be is that maybe this event was rupturing different parts of the fault than we're rupturing in the 1952 earthquake. So to look at that, we could look at the overlap between the 1952 event and the 2025 event. So here's just a little bit of an animation with the 1952 event shown in gray to white on the back with high slip indicated by darker colors. And then overlaid on it are contours of our latest slip model. And you can see there's actually quite strong overlap between these two slip distributions. So, you know, there's a lot of caveats here. Our slip inversions are relatively insensitive to slip at the trench, and they're relatively insensitive to small scale variations. But there's certainly a lot of similarities between these two events. So together, this kind of shows that these megathrust events can happen on the same sections of a subduction zone more often than we may have previously believed, which obviously has big implications for hazard and risk. Okay, so takeaways. The 2025 event was a relatively shallow unilateral rupture, which included large peak slip to the southwest. Damage from the shaking was limited by the sparse nearby population in the region. The 2025 rupture has many similarities to the 1952 rupture, but it's not totally clear yet whether it's re-rupturing the same parts of the fault or not. And finally, megathrust events can happen on the same sections of a subduction zone more often than we may have previously believed. So with that, I'll just plug, we have a paper that John mentioned that was just published in the Seismic Record, and it's open access if anyone wants to take a look at it for more details. And hopefully we'll have some time to discuss at the end. So thanks so much.
Thank you, Zoe. That was wonderful and a great overview and thought-provoking there. So yeah, we will save questions for the end, but I invite you to look in the chat. You've already got some questions coming. So thanks so much. That was great.